profile. Like if you complete a certain number of exercises, then you get these badges. That ties into the point again about gamifying learning. Like it becomes a game of how many points can I get on my account by doing these exercises, rather than how much like CS can I learn. And that also ties into another point that I'm going to get into later. But most of the work has been done for us. Like there are people investing a lot of time and money into creating the most like easy ways for students to learn computer science. So things like Khan Academy, App Inventor are extremely like useful to know that those exist. Okay, in the interest of time, we're going to move on. So we're going to talk about the actual fundamentals I alluded to earlier. So the 5 that we're going to talk about, and are probably the only ones you need to worry about for most Intro CS classes, are 1, algorithms, 2, loops, 3, conditionals, 4, variables, 5, functions, or abstraction. And we're going to go into all these in a little bit more detail. And you probably are familiar with several of these terms, or probably all of these terms, if you, like not even in a CS context, but like in math or in just like everyday, like everyone knows the word like loops, for example. And so we're going to talk about them in a CS context and just recognize that there aren't a lot of words that we need to know. There's not a huge knowledge barrier to CS. And these are all on the worksheet too that I think you all got. So in addition to talking about fundamentals, I want to mention the idea of programmatic thinking. I'm going to confess, I don't think this is an actual term. I think what Nathaniel used about computational thinking is like the real term. But basically, so like on the slide is a lot of information, but the idea is that, right, so we're going to talk about the fundamentals, but those aren't like the core hurdle that your students are going to have when learning computer science. The core hurdle is the attitude and the mindset that you have when you approach problems. So just going, like reading what we have on the slide, break the problem into smaller pieces. If you have a huge like app that you want to build that, I don't know, maybe organizes your classes or something like that, that's a lot of steps. Like you can't like just jump into that. And it's pretty intimidating if you haven't tried something like that before. So the idea of trying to break things into smaller pieces, the idea of debugging or making small changes. So like say your code doesn't work. Like what do? You have to, you can't like just like stare at the code and kind of wait for the revelation to come to you. Like we try to emphasize, and you can't. This is something that you can't really teach, because students have to realize for themselves. You have to just start. You have to try and realize where the problem is, and make changes rather than staring at code, which is like easier said than done. It's very easy to get frustrated with code that doesn't work. And the third point here is perseverance. This is something that I like continually find in my classes, like here at Yale. But CS is very unforgiving. Like you can have tests that you want your code to pass. Like for example, is this returning the number that I want? And it doesn't work. And the computer doesn't tell you why, because the computer doesn't know why. And then you don't know why. So like it's like I put all this effort in and my code isn't working and I don't know why. And it's sometimes hard for other people to help you because maybe you put so much work into your code base. People don't understand. People aren't familiar with it, so it's a skill of perseverance to be able to go back into your code base and figure out what's wrong. Like it requires a lot of like emotional perseverance, and it's an iterative process. Like you have to keep like finding out what's wrong and trying to work based on that. So I just want to break down like what kind of stuff our syllabus covers, so you have a kind of a sense of what we're mostly doing in these classes. Our class is 15 weeks, so these are all 1-hour sessions. And by the end of this class, you have students on App Inventor like making their own apps independently, like the last 4 weeks of our project. But the main thing I want to point out is that if you look at the key on the right, you have yellow algorithms, blue conditionals, green variables. The top 3, the algorithms, conditions, and variables, are the actual like concepts that you are teaching explicitly. And those are only 4 out of the 15 lessons that we're teaching. So like 4 out of 15, that's not a lot. The rest of these are just projects that we assign, and for most of these class periods, the students are just set on their own or in pairs with their mentors, and they're working on these projects on their own. They're struggling, they're running into bugs, they're trying to fix what goes wrong, and this goes back to like how we believe that's the most effective way for these students to learn. We make this, that's why we have so much project and building in our classes versus a lot of teaching. Any questions before I go on to the next section? Awesome. So how do, like the bread and butter, how do you actually teach these things in a classroom? So I'm going to show you guys an example of a lesson plan that we would actually use, just so you know how we break down the 1 hour that we have. It's a little small. So this is for an app that we do in our second week of classes called Hello Purr. It's literally like a cat on a screen, and you tap the cat and it makes a purring noise. Pretty simple, but like it's pretty satisfying for these kids for the first time to make their app, and when they touch it, it like responds to them. It's a physical response. So the first 5 minutes would just be like we're coming into a classroom. Hi, how are you? How was your week? Like, would you remember what we did last week? For minute 5 to minute 30, we are splitting into our mentor groups. So one mentor per 4 or 5 students, and they just have at the problem. Like maybe we'll give them a worksheet that explains what the code, what their assignment is. But other than that, they're basically set on their own and are struggling with problems, asking questions when they run into problems. At minute like 30 to 35, we'll say, all right, everyone check in up at the front of the class, raise hands for like what questions you have, like what's hard, how far are you? Just so that they're not completely set on their own, so that they know that where other people are and where they can get help from. And then at the end, we just continue basically for the rest of the class to continue coding. You'll find that a lot of students like breeze through these exercises, like a lot of students that are comfortable with computers or are good with math, or maybe have had experience with this type of thing before, will breeze through your exercises and finish them quickly, whereas others will like need a lot more time. So there's a lot of ways you could address that. There's like having the students that finish quickly help the students that are not finished yet. What we do a lot is we come up with extra exercises to keep those kids occupied that finish early. Like for example, okay, you made your Hello Purr app, and when you click on the cat, it makes a purr noise. Can you, on your own, find a picture of a dog, put a dog button on your app, and then make it do a dog noise? Like, just, they're easy to think of, but they are challenges for the kids to do, and they also, and they're so that they're making the most of their time. One more thing that we often do is we have these things called maker cards. The curriculum that we use from CS and SF, I will talk about that later, but these are cards, each of which has some sort of task. Like, so you could maybe have a physical deck in your classroom, and they say, okay, you're done with your work, take a maker card. Let's say they do number 3. We've actually done this one in class. Make your phone speak to you. Type a phrase in a text box. Then press a button and use the text-to-speech component to let the phone speak the text that was typed. So like when our kids finish early, we'd say, take this maker card and just build this. Like no other instructions, you know what to do. Just go ahead and try and see if you can make this product. And having this sort of, and this is something that like kids find extremely fun, because like it's something that you can customize, you can type in whatever you want. A lot of kids just like will have at it with the curse words, so you have to kind of put a censor on that. But it tends to be just the idea of having these things that can keep these kids these challenges in case people finish early. Alright, so now we're going to get into actual activities that we do. So the first one is based on algorithms. An algorithm, as you probably know, is a list of steps that you can follow to finish a task. So the activity that we use for algorithms in classrooms is this gift wrapping challenge. You might have seen a variation of it before. Basically what we do is we have 2 robots. 3 robots. Okay, so I guess you guys can come up here where it's visible. We have a box, and we have some wrapping paper, and we have tape. And what we have students, or in this case you guys do, is everyone gives one instruction at a time. The goal is to instruct these robots, who are computers, who have no like prior knowledge of it, like except for basic English, but have no knowledge of the world or of wrapping presents. You have to tell them exactly how to wrap this gift. And again, the materials we have are a box and a lid, wrapping paper, a bow, tape, and scissors. So if I can get like volunteers, like one at a time, just shout out an instruction, like how should we wrap this present?
Unfold wrapping paper.
Okay, unfold wrapping paper.
Put
Okay.
the top on the box.
Put the top on the box. Okay, so that didn't go as planned. Yes?
to take the top and fit it to close the box. Flip the
What's
flip
close?
the top over.
What does close mean?
Can people over there see?
Forbid.
Okay, we got turn the lid.
90 degrees.
Rotate the lid
By how many degrees?
by 90 degrees.
Pick up off floor.
All right, let's keep going. I think we can get this. So it's kind of
Make sure
Yes.
the lid fits evenly around the rectangular shape.
Make sure the lid fits evenly around the rectangular shape.
You were on top. Why did you move
Don't yell
So
at
these
me.
are not smart robots.
So we'll jump to